All right, next comes heap. Ooh, a little off. They are allocated and deallocated as the programs run. They are not associated with any specific event. So the stack was directly associated with calling a function. The heap will not be. Sorry, that's a little low, but it'll make some sense in a little while. The kind of data found on the heap depends on the language. There are some languages that just store everything on the heap. There are some languages that avoid as much as they can putting stuff on the heap, and then you got different policies going on. Special operations are needed. In procedural, y'all never did new and delete, did y'all?
No.
No. But in Java, you did new, right?
Yes.
So new is adding something to the heap. So I'm going to go up here, and I'm going to say int let's go pointer I. We'll get to what that means in a moment. New int. I'm going to call it sub 100. What is that doing? This is actually very important.
It's making an int array in the heap.
Correct. That's one thing it does. What's stored on the stack?
The pointer to the array?
Yes. So int star I is on the stack. When your program begins, it's unknown. It's undefined, sorry. But when you're at this line of code and you execute it, what happens is it allocates, we'll just say down here, 100 ints, and this I variable is going to contain a memory address. We'll say 0x, and I'm going to be super lazy and just call it ff08. We'll say that this is 0xff08 is the start right here. I'll just say for sake of laziness, this is 0. So this variable actually contains the memory address. It does not contain the array. That variable does not contain the array. It contains the location of where the array is stored. The reason I write this out this way is so that when I start showing this, that memory location points to there, but keep in mind that that variable is only storing a memory location. It's not actually creating this point. What creates that point is the compiler using it as a pointer so that it knows to jump to it. Are we okay with that? All right. Tapping around. Space, all right, so in the last class we talked about new and delete, where you had to delete it, otherwise Valgrind reported a memory leak. We did go through that, I believe. Yes. Good. Space is allocated in variable size blocks, so deallocation may leaves whole, called fragmentation. Oh, what does that mean? Well, let me paint the picture real quick. So you allocate and you deallocate. The heap generally starts at the bottom and grows up. So you may allocate 100 ints, may allocate another 100 ints, may allocate another 100 ints, and then all of a sudden you decide to deallocate these ints. Notice I'm not showing pointers. The heap has to actually manage that this is allocated, this has been deallocated, this has been allocated, and it has to manually find out where it is. Right now, there's a hole, right? Here's the problem. 100 ints, this was 100 ints and got freed. Now I want to allocate 200 ints. Where does it go?
Above and below one of the 100 ints?
Can I put it here?
No.
No, it has to go up here. And let's say for the sake of arguments that there's memory storage for 100 integers right there. And there's memory storage, this is deallocated, for 100 ints right here. Let's say I want to allocate memory for 150 integers. Is there 150 integers of deallocated space?
Yeah.
Yes. There's 100 here and 100 there. Can I allocate an array of 150 integers? No. I cannot. Would this ever happen with the stack? No. Why does it never happen with the stack?
Because it only adds things at the bottom and then takes them away.
Right. The stack never deallocates from the middle. It only operates at the end. So it grows and shrinks. Well, if that's the case, why do we have a heap? Why don't we just use the stack for everything? If you're doing a database with records of students, you don't know what the size of those students are. You just need to create that. You need to allocate the students on the heap, pass it around a bunch to all these different functions, which may grow and shrink depending on what you're doing with that student. And when you're finally done with that student record or object, then you deallocate it. With the function, it's like, okay, I need you to do this temporary work. All right, we're done. Do this temporary work. Okay, we're done. Now, is it technically feasible that we could engineer our program so that we don't have to use the heap? Yes. But it would be very cumbersome very quickly. Especially if you need to have a bunch of global data storing around, and it gets really messy trying to add a bunch of functions that would be unnecessary. So the heap is very useful, and I would say is necessary for performance. Otherwise, you'd have to deal a lot with allocating functions needlessly. That may be a little hard to understand right now. That's okay, but we have a heap. All right, so languages leave the heap storage deallocation to the programmer. Did I ask you why C++ does this? Oh, did we? Okay, real quick. Why does it do it?
For performance.
Performance, yeah. Or performance and power. So if you want to be able to manage it yourself, depending on what you're working on. So an embedded system really can't run a garbage collector. You have to deallocate yourself. Plus, an embedded system may have a special memory system inside of it that's not the norm, so you need to be able to utilize that yourself as opposed to using a standard one. Right, so Perl, Java, Perl, Python, list-based programming language employ garbage collection to reclaim unused heap space. Great. Here's the picture that I drew on the board. There's the static area up top, there's the stack, and there's the heap. They start at 0 and go to n, and this is a common way to look at it. The reason we're doing this picture is because this is how the C programming language and almost all programming languages, this is the model of memory that you work with. I'm going to tell you right now, this is not how it's implemented in hardware. That's okay, because everyone agrees that for a programmer, you think of memory like this. And the hardware is going to give you the illusion that memory works like this. For this course, this is how memory works. We'll get to the other stuff later. The following must hold. All right, so what were these variables? We already forgot what they were. 0 is the top, A is the end of the stack, H is the beginning of the heap, and N is the end of the heap or the end of memory. So remember, A is the end of the stack, H is the beginning of the heap. So hopefully A is greater than or equal to 0, which is less than or equal to the beginning of the heap, which is hopefully less than or equal to your total memory. In other words, if the stack bumps into the heap or if the beginning of the heap is greater than the end, there are problems. What type of problem would this be?
Stack overflow.
Okay, stack overflow. Oh, it's labeled right up top. Huh. Good job. All right, nice. Literacy. Okay. Wins again. Woo! Like, wow, y'all got to that quick. All right, we talked about different heap management functions. We talked about delete, and we will be doing that a lot more. We're going to get plenty of practice with delete. Let's see, heap overflow occurs when you call a new and the heap does not have enough contiguous blocks of unused k, so the new either fails, calls the heap overflow, or returns the pointer to the new block. Wow. Okay. Right, so if the heap is growing up, and the heap grows into the stack, then that's a heap overflow. So what is a new return? Almost none of y'all are ever going to check new, and you're just going to assume that it works. Unless we're dealing with a super real-time system or a medical device, that's perfectly fine for now. I'm not going to make y'all check new all the time, although it is a good habit. So new either fails, returns, in general it will return 0, a null pointer. By the way, why do we choose 0 as a failure?
Because in my way, it's never actually going to return, have a pointer of 0.
And why would that be? You're correct. At least in the environments that we use.
The operating system.
Yeah, that's where the OS is, yeah. And if you could write to 0, then we got problems. Because that means your program can overwrite the OS. Which, by the way, back in the days of DOS, that was completely legal. No problems. Just go right ahead, overwrite that entire thing. No problem. Sure, do it. But nowadays, the operating system will stop you. They usually call a segmentation fault. Hey, any of y'all gotten that one yet? Seg fault? Well, you will. Fails in the case of heap overflow, returns a pointer to the new block if it can allocate it. Great. Delete, freeze it. So if we were over here and we want to, ooh, that's cool. Delete I. Actually, we want to do that. Oh, let's go to the board. This is also a very important thing. At this point, what does our memory look like? Well, let me erase this because it doesn't actually exist. That never existed. All that happens at this point is this is de-allocated. I's value is not changed. I still points to the memory location of where those 100 integers were. What do you think happens if you try and write to those 100 integers after you have deleted it?
Is that a seg fault?
It should be a seg fault, yes. Hopefully, I mean that literally, hopefully the operating system stops you. It may not. But hopefully it says use after free error detected. If the OS does not, Valgrind will tell you. It depends on a lot of situations. If you just delete it and then I write to it, I'm pretty sure it doesn't stop me. Yeah, it doesn't stop me. That is bad. That is a huge error. And it didn't tell you anything. But Valgrind would, and just to show you, actually Valgrind's going to yell at us. Invalid write of size 4. And if I did a G, it would have, is 0 bytes inside of a block size of 400 freed. So it says you had these 400 bytes, and then you freed them, and then you tried to write to them. That's what you did wrong. Well, what were those 400 bytes? Well, it was 100 integers because 100 integers, each integer consumes 4 bytes. 100 times 4 is 400, so there it is. Yeah. Just warning you of the dangers because they're all coming. All right.